This video will demonstrate how to design a composite steel beam in VisualAnalysis that is shored during construction. Check out the other training videos to learn how to design beams that are unshored during construction, or for an overview of composite beam design in VisualAnalysis. Let's get started. To effectively use VisualAnalysis to design composite beam members, only the steel members should be modeled. The stiffness from the concrete slab and from the member offsets should not be included in the model, as these will be automatically accounted for in the design checks. In this example, we will look at a simply supported beam that is 45 feet long. The W21x50 beam has already been drawn with a pinned roller boundary condition. In the dead load case, both a uniform load and a point load 2.5 feet from midspan have been applied. The applied dead loads include the self-weight of the steel beam, the concrete deck, the metal deck form, and any other dead loads on the system. A uniform load and a point load 2.5 feet from midspan have also been applied in the live load case. With the member created and the loads applied, we will now set up the load combinations in the load case manager. We will select the ASCE 716 LRFD load combinations. We will also select the deflection checks. Switching to the result view, we can see the analysis results for the various load combinations. The deflections for these analysis results appear large since they were computed using the moment of inertia for the non-composite beam. Prior to performing the deflection checks, these results will be scaled by the ratio of the beam's moment of inertia to the lower bound moment of inertia to account for the composite stiffness of the beam and slab system. Switching to the design view, we will select the beam and mark it as composite. This causes additional sections in the Modify tab to appear so that the parameters for the concrete slab, the deck, and the anchors can be specified. First, we will select the deflection limits using the default member span ratios. Next, under the concrete slab section, we see that the construction type is shored, which is correct. For our case, let's use a 7.5 inch thick slab and assume that the beams are spaced at 10 feet or 120 inches on center. Next, we can set the deck type to have ribs that are perpendicular to the span of the beam. The deck parameters can be entered manually, or a deck profile can be chosen from the database. We will choose a 3 VLI 22 gauge deck. Finally, let's define the steel anchors to connect the slab to the beam. Either channels or studs can be used for the anchors. We will use 3/4 inch diameter headed studs with a strength of 65 KSI. The studs will be 4.5 inches long and will be spaced at least 2 inches from the web of the steel deck. We will start out with one row of studs for the beam. In VisualAnalysis, the member can be divided into multiple regions and the stud spacing can be set for each region of the beam. For our example, we will just have one region and we will specify a 12-inch stud spacing. Clicking OK, we now look at the beam and see that the unity exceeds 1, which means that the beam has failed. Hovering over the beam, we see that the controlling limit state is the strong deflection check for the dead load plus live load case. To increase the stiffness of the composite beam, we could use a larger steel cross-section, or we can simply use more anchors since the lower bound moment of inertia depends on the capacity and the number of anchors used. For our case, we can simply increase the number of studs by using 2 rows instead of a single row. With 2 rows specified, the unity of the member reduces to less than 1, and now the design passes. Double-clicking on the member produces its report. In this report, we see a summary of the parameters that we specified for the concrete slab, the deck, and the anchors. We also see that the detail column provides some useful information, including intermediate values that were used in the checks. The strong deflection details include the lower bound moment of inertia, the pre-composite deflections, which are 0, and the composite deflections. The composite beam details show the anchor strength, the effective slab width, the effective slab thickness, and the effective number of studs used to calculate the composite capacity. Since we have a significant number of effective studs, the beam is able to achieve full composite behavior at this particular offset. The unity checks are less than 1 for both the strong deflection check and the composite beam check. Therefore, this beam passes. In just a few minutes, we have used VisualAnalysis to design a composite steel beam that was shored during construction. Check out the other training videos to learn how to design beams that are unshored during construction, or for an overview of composite beam design and visual analysis. Thank you for watching and have a great day.